Welcome to another class of multivariable calculus. Today the topic is surface area. So our question is, we come across many times this diagram. So we are having a solid over here. We are having a solid and its equation is given by z equal to f of xy, and we want to find the surface area of that solid. This is the surface is given. We want to measure what is this surface area. This area we want to measure it. Okay, now how to measure it? Only through approximation only. So for that, what we are considering is, first of all, in our usual system we should consider a rectangle. Okay, so that rectangle, we can have the rectangular set of all xy such that some a less than or equal to or x less than or equal to or b and c less than or equal to y less than or equal to d. So as our usual custom, you are denoting a rectangle. From here we will split this into so many rectangles and we will consider one such area, that is Rij. So we will consider one such area as this Rij, light green colored portion. Now above this we can have a surface like this. So we want to measure the surface area of that surface. See, like this. So how to measure the surface area? Again we are going for an approximation. We will consider the tangent plane over here. Okay, so we can have a tangent plane over here. Now this tangent plane, we can have something like a projection and all. We will have from here to here and here to here. If you are projecting this, you can have a rectangular or a parallelogram over here. Now we can easily find the area of this parallelogram and we'll approximate that to the surface of this required region. This is the main idea that we are using. So we are having the tangent plane idea. This, if you are mentioning this as an Sij, we can express this as delta Sij. So this small portion we can express as Sij. Then the entire area means sigma I equal to 1 to m, sigma j equal to 1 to n, delta Sij. Right? Now how to find or how to approximate this? That is through tangential planes. So we will mention this tangent plane as Tij. So this one we will mention as Tij and its area as delta Tij. So delta Tij. So delta Tij is approximately equal to delta Sij. But in order to have this approximation to a greater accuracy, we will have the Tij in the direction like this. See, Tij, let A and B be vectors that have initial point xi by j, f xi by j. That is the rectangles, bottom rectangles. This portion we have projected, and in the surface we will have something like that. One surface we have got now. So this surface contains the point. This point is that xi by j, f of xi by j, right, and lie along the sides of the approximated parallelogram. So in the above we can consider the parallelogram like this. Okay, so above that we will have a parallelogram, right? So above that we are considering the parallelogram. See, now according to this point, or with reference to this point, here also we are having a point here, right, and lie along the sides of the approximating parallelogram. Now from previous section we have the slope of the tangent lines passing through xi yj f xi yj and having directions a and b are given by fx xi yj and fy xi yj. Therefore, we can have our a as delta xi into fx y xi yj into delta x times k, one direction, and b as delta yj into fy xi yj into delta yk. Right? Now we can have the cross product of these two, that is nothing but the area, because this is a is going to be one side, a is this side and b is this side. So area is going to be the cross product you can have, right? So we can have the cross product delta Tij is equal to a cross b we want to find, then find its modulus, right? Now a cross b is given by ijk. You know how to find this. Take the determinant of this matrix, you will get the answer like this. So delta a is common. Now delta a can be replaced as delta x into delta y in the area of Rij. Therefore, delta Tij will become square root of, we want to take the modulus now, so square root of fx xi yj square plus fy xi yj square plus 1 whole into delta a. Exactly, if you are having a bracket here, it should be much more clear, right? Plus 1 into delta a, because k, modulus of k is 1, so 1 into delta a we will get. Now we can have this formula like this. Thus we can have the Riemann sum, and when n and m tends to infinity, we will get the double integral. So a is equal to, if f is defined on a region R in the xy plane, and suppose that fx and fy are continuous, the area A of the surface z equal to f of xy is a equal to double integral over R square root of you are having fx xy square and fy xy square plus 1 into delta a. So let us see one example here. Find the area of part of the surface with equation z equal to 2x plus y square that lies directly above the triangular region R in the xy plane with vertices 0, 0. So we can plot it. So I should be the rectangle, or sorry, triangle 0, 0. Here is the point 1, 1 and 0, 1, 0, 1 somewhere here. So this is our triangle. Like so, like this we will get it. So our region is x is lying from, see, this is x lying from 0 to this line. This line is y equal to x. So 0 to x, sorry, 0 to y, and y is ranging from 0 to 1, 0 to 1. So this is our rectangle we can consider. Now using equation 3, that means the formula for finding area, we can have the area as a is equal to a square root of partial derivative with respect to x square, partial derivative with respect to y square plus 1 into delta a or dA. And this is equal to fx. You can easily find it out as what is fx is coming? Fx is equal to 2 and fy is equal to 2y. Right? So 2 square plus 2y square plus 1 will come. So you can have 2 square plus 1, 5 and 4y square here. So just we want to integrate this. Say C1, you can directly go for the integration. So you get it as, if you want means you can go for substitution also. So you can have 4y square plus 5 equal to some u, then 8y, right? 8y dy is equal to, oh, no need of here, right? We are directly going for x, right? No need here. So you can go for integration over here. You will get x into square root of 4y square plus y, x equal to 0 to x equal to y. So you will get y into this. Now in this case you can go for substitution, right? So it will be 8y dy is equal to du. then your y is ranging from 0 to 1. So y is ranging from 0 to 1 means you can take the variation of u also. Just you want to substitute that, you will get the answer as 1 by 12 into 27 minus 5 into root 5. So second example, find the surface area of a part of the paraboloid z equal to 9 minus x square minus y square that lies above the plane z equal to 5. So that lies above the plane. So if you want to plot it means picture will be like this. Okay, now using the formula, the formula is this. So fx, here fx is going to be our function is going to be like this, right? So fx value is going to be minus 2x and fy is going to be minus 2y, right? Now this you want to substitute here. We are getting 4x square plus 4y square plus 1 into dr. This can be replaced with your polar equations, then it should be easy. So 4 into r square plus 1 into r dr d theta you will get. Yes. Now it is range is selected because range is from theta is from 0 to 2 pi into rotation, right? And your r value is running from r is like this, right? 0 to 2. 0 to 2 it lies. R value exactly minus 2 to 2 will come. Then you can integrate that. So we get 1 by 6 pi into 17 root 17 minus 1. Okay, see here the picture is given z equal to 5, so we get something like this. Now up to here to here we have used the polar coordinates there for the easy purpose, right? So here also we can go for substitution. 4r square plus 1 is equal to some du, some u, and 8r is equal to dr is equal to du. Just you want to substitute that, we will get the answer like this. Now area of surface with equations. Suppose the equations are given. So y equal to gxz is given. That means it is in the xz plane, right? And if x equal to h of yz, that means that is in the yz plane. In that two cases, we can modify our formula like this. So g be defined on a region R in the xz plane. Let me change this ink. Okay. Suppose it is in the xz plane, and suppose that gx and gz are continuous, then the area A of a surface y equal to gxz is given like this. So gx, gz. Only that's the difference here. So similarly, if yz means it should be hy and hz. So we can calculate like this. Find the area of that part of the plane y plus z equal to 2 inside the cylinder x square plus z square equal to 1. See, given as x and z. So it will be gx and gz. So g is given. See, is given. Go for gx and gz. You are having the value like this, and plus 1 into dA. That is, you will get root 2, right? So root 2 into double integral over 1 dA. That is, we'll get that to be as root 2 pi. See, like this. Okay, go for substitution or in polar coordinates, you try this. So if you're not getting root 2 pi means ask me how we can do it. And if you're finding any doubt, please ask me what's your doubt means, then let me clarify it. Okay, so thank you for your patient listening. Thank you.